Hello, my name is Corey Marcus, and I'm a PhD student working with Dr. Renato Zanetti at the University of Texas at Austin. Today, I'll be telling you about our work, Direct Visual SLAM with a filter-based LIDAR measurement incorporation. We have modified an existing direct SLAM algorithm to accept LIDAR range measurements. We integrate the measurements through an EKF and clever use of the gamma and inverse gamma probability distributions. SLAM has a lot of cool applications in spaceflight. These include situations such as proximity operations with both man-made and natural satellites, or a situation where you would have a lander which would like to identify landing sites autonomously. In the image, we see the well-known Curiosity rover landing with its sky crane. Now, this mission did not use SLAM since the engineers had prior knowledge of the landing site, but someday in the future, other missions may decide to use SLAM so they can choose sites which are less well known or contain many obstacles. Many SLAM systems in the literature are monocular. This is due to the abundance of information in a camera image as well as the relative cheapness of monocular camera systems. We are all familiar with the common feature-based SLAM systems. These use algorithms like ORB, SIRFT, or SIFT to track common geometric features from one image to the next. But there is an alternative. Direct SLAM systems align images through direct alignment of local pixel intensity gradients. Usually, any pixel can become a map point. This causes direct SLAM maps to usually be denser than their feature-based counterparts. Unfortunately, we cannot observe the true scale of an image with a camera alone. We need a sensor which produces measurements with some unit associated. Traditionally, LIDAR involves either a single point or a small number of points. These sensors can be fixed or mounted on a rotating gimbal. Flash LIDAR is an emerging technology which takes a whole bunch of measurements, either simultaneously or almost simultaneously. These measurements are structured in a grid. As other authors have noted, direct SLAM is a better choice for LIDAR integration than feature-based. Because the density of the map increases, your chance of LIDAR measurements impinging on a map point directly. Several other authors have created work similar to ours, direct monocular SLAM plus LIDAR SLAM. But they incorporate LIDAR measurements into their nonlinearly square scheme and discard measurements which do not closely align with a map point. I want to briefly cover a probability distribution family which we leverage heavily in this work, the gamma and inverse gamma distributions. The most important thing to note here is that if a random variable is distributed according to one, its inverse is distributed exactly according to the other. This means that if we know the moments of one, then we exactly know the moments of the other. Now I'd like to briefly show you that if you have a Gaussian random variable with a positive mean and relatively low variance, then both the gamma and inverse gamma distributions with the same mean and variance are fairly good approximations of this Gaussian. This means that if we have a random variable which is distributed according to a Gaussian, and we would like to understand the moments of the inverse of this random variable, we may obtain these analytically by first approximating the distribution as gamma or inverse gamma. If we did not do this approximation, we would encounter significant difficulty due to the non-zero chance that any Gaussian random variable's true value is 0. LSD-SLAM is a fairly well-known open-source direct SLAM algorithm. As I mentioned before, this means that pixel depths are estimated directly, without feature matching. The map is divided into a series of submaps which are anchored on selected camera images known as keyframes. One interesting quirk of LSD-SLAM is that the map representation contains estimates of inverse depth. This is what necessitates the previous discussion of gamma distributions. We have modified LSD-SLAM to accept range LIDAR measurements specified by an azimuth and an elevation. We assume that this LIDAR system is exactly co-located with the camera and that each camera image corresponds to a LIDAR image. We use the measurements to perform 3 primary tasks. We initialize the system, we estimate the scale of the map, and we update the map. On the bottom, we outline the map refinement process. First, a new keyframe is created, and then the scale is initialized. We've written that code. Then the camera image is used to update the map, followed by our LIDAR. And this process is repeated until a new keyframe is created. LSD-SLAM chooses to initialize the depths of all pixels randomly. We choose to use each LIDAR measurement to initialize the corresponding pixel's inverse depth estimate. This is done by approximating the measurement as an inverse gamma distribution. The mean is the measurement and the variance is the measurement noise. Now, the mean and variance of the inverse depth estimate are known analytically. One additional complication is the fact that we need a scaling factor, K, to preserve the fact that LSD-SLAM expects the average inverse depth estimate to be 1. LSD-SLAM initializes a new keyframe by propagating points from the previous one into the new one. We use these propagated points in the LIDAR measurements at this new keyframe to estimate its scale. We can form a measurement of scale, beta, as shown. Then our scale estimate is a simple maximum likelihood estimate of this Gaussian sum. By assuming the inverse depth estimate, each camera image after the keyframe is used to estimate camera pose and update the map. We can use these estimates to associate a LIDAR measurement with a pixel in the keyframe. If this pixel has an estimated inverse depth, an EKF update will be performed. We could use the predicted measurement shown as a function of the inverse depth for our EKF, but instead we once again leverage the gamma distribution. By assuming the inverse depth estimate is gamma, the depth estimate is analytic and inverse gamma. This reduces nonlinearity of the measurement dynamics and qualitatively improves EKF performance. We update the depth estimate with an EKF and then use our known relationships to transform this updated depth estimate into an updated inverse depth estimate. If there is no valid estimate corresponding to the LIDAR measurement, we can initialize one. We assume that the measurement is distributed according to an inverse gamma, and then initialize the inverse depth estimate as a linear transformation of the gamma distribution. LSD-SLAM employs a map smoothing algorithm after each cycle to reflect the tight correlation between depth estimates of adjacent pixels. The smoothing algorithm is essentially a Gaussian blur, but with some minor tweaks to handle the variance estimates after smoothing. We employ the same smoothing algorithm after LIDAR updates. This allows LIDAR measurements to indirectly update many additional points. We've created a SLAM simulation environment tool outputting RGB and LIDAR images. With this, we've performed 1,000 iteration Monte Carlo with and without LIDAR map updates. On the left, we see one of these example RGB images, while on the right, we see an example LIDAR range image, which has been provided false color to represent depth. LIDAR updates result in a higher quality map. Here we see the average depth estimate error reduction for all Monte Carlo runs and for all updates. On average, 200 points are directly updated, and the error in depth estimate is reduced by 3 to 8 centimeters. If we look at the same plot after the smoothing algorithm, we can see that between 5,000 points and 15,000 points are updated for an average error reduction of 1/2 to 1 centimeter. We can see that a higher quality map results in higher quality position estimation. Here, the black lines demonstrate position estimation error with LIDAR, while the red shows it without. On average, the position estimate error is lower with LIDAR than without. We see a similar story in attitude estimation. Again, attitude estimate errors are lower with LIDAR updates than without. The European Robotics Challenge dataset contains the European Robotics Challenge dataset is a nice UAV dataset with stereo camera, IMU, and Vicon measurements as the UAV navigates a small indoor space. In addition, they provide a forward and backward smoothing best estimate of pose from a fusion of the Vicon and IMU data, as well as a dense 3D scan of the environment. We can use these estimates of truth to create simulated flash LiDAR images, which are co-located with one of the cameras in the dataset. Then we run our algorithm on this dataset at 20 Hertz on a Dell Optiflex workstation. With our LiDAR updates, we see greatly improved tracking performance. Note the blue position history with LiDAR agrees much better with a black truth than the red trace without LiDAR. We even have better robustness. Without LiDAR, the system loses tracking at about 90 seconds due to fast UAV motion. With LiDAR, the system has no problem tracking through this segment of the flight. Tracking is momentarily lost with LiDAR at the end of the flight. This is due to a large portion of the camera's field of view being obscured by the landing surface as the UAV lands. Now, I'd like to show you a demonstration of our system on the EuRoC dataset. This video is available on YouTube if you'd like to see. You can see on the left estimates of the current keyframes map. Note the way that the LiDAR images greatly fill in the center of the map as new measurements are acquired. On the right, we see a visualization of the global map, as well as the pose estimate of the camera within that global map. Note the really good density and accuracy of this global map with LSD-SLAM plus LIDAR updates. I'm sorry. The blue boxes represent keyframe locations, while the red box that you can see in the visualizer represents the current pose estimate. Green lines are known or implied relationships between different keyframes. This visualization software all is included as part of the open source LSD-SLAM software. You'll notice as we come into land, the camera, a lot of it is obscured and we do lose tracking. Right there, tracking was lost because of that landing surface obscuring the camera. The map will continue to shift as the system closes out and it does any final refinements. And that's all I've got. Thank you so much for watching. I look forward to seeing you guys all during the conference.